In this video, we're going to be diving into correlation and discussing when it's appropriate to do a test of correlation, reminding you kind of how do you even calculate this stuff, and talking about what we can take out of it. So there's several kinds of correlation. I'm not sure how much you've talked about this, but there's at least three kinds. There's actually many more. But three common kinds, I'll say. One is Pearson's correlation. This is the traditional correlation coefficient, and if you've never heard of any of these, then Pearson's is the one you know. A couple other non-parametric versions are Spearman's, pretty common, and Kendall's tau. These all have different letters. Pearson has R and rho, technically. Spearman's rho is his statistic, and then Kendall's tau. But for this video and in this review, we'll focus on Pearson's. And if you're interested in Spearman or Kendall, check out non-parametric, or I think we even talk about Spearman's correlation in our regression class. So the types of variables that we need for Pearson's correlation are a continuous independent variable and a continuous dependent variable. So for instance, age and height are two continuous variables, and we might say, is there a relationship between age and height? Now, with all of these, it's important to realize that there are assumptions that we make. So as part of these assumptions, just realize that there's some assumptions in the background, and we're going to spend some time later in the analyses that we're going to focus on in this class talking about those assumptions. But one of the assumptions of a Pearson's correlation is that we're looking not just at a relationship between age and height, but at a linear relationship between age and height. And this is actually kind of an important distinction. So how we write our hypotheses are as this funky looking p equals 0, where the funky looking p is not equal to 0. So the funky looking p is the Pearson correlation coefficient at the population level. So typically Pearson's is written as R, and that's probably how you've seen it. But at the population level, the value is rho. Incidentally, there's a minor point to bring up here that overall, the population level statistics are written in Greek, so like rho, whereas the sample statistics are written in Latin characters like R. So I should note, just like we talked about previously, this can also be written not just with rho equal to 0, but with rho equal to k. So we could do this with, is the correlation 0 versus is the correlation not 0? That's asking if there is any linear relationship at all, but usually that's not what we care about. So if I told you there's a linear relationship of 0.000000001, maybe you don't particularly care. However, if I could turn around and say, actually, I have evidence that the nature of the relationship, or that the relationship is stronger than 0.3, the minimum amount you care about, well then that might be much more meaningful, or much more meaningful to know or test against. So that is something that's available here, is that you can rewrite these statistics and this statistic as well in rho equal to k and test that instead. So for the test statistic, first of all, recall how we calculate the sample Pearson's correlation coefficient R. So it's the sum of x minus x bar times y minus y bar divided by the square root of x minus x bar squared, and then all summed up, times y minus y bar squared, and then all summed up. So this is how we calculate the correlation coefficient. One of the ways, there's multiple formulas you can use. But this is important because the test statistic for the correlation depends on you being able to calculate the correlation, and we'll actually demonstrate this a bit in our code when we get to the R section. So the test statistic is going to be t equals the correlation times the square root of n minus 2 divided by the square root of 1 minus r squared, and it's distributed as a t-distribution with n minus 2 degrees of freedom. So how many observations do you have? N minus 2. So that is, and again, it's the same thing. The test statistic t is distributed as a t-distribution with n minus 2 degrees of freedom, and again, for the critical value, we'd be looking at 1 minus alpha over 2 for a two-tailed test. The decision, surprise, 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 is if the test statistic is in the critical region, or if we're using the p-value method, if p is less than alpha, then we reject the null hypothesis. And if not, we fail to reject the null hypothesis. And it really is that straightforward. So with the correlation, the big challenge is calculating the correlation and also remembering that the correlation is purely about a linear relationship. One more thing about the correlation that you can recall is the coefficient of determination. So if I square the correlation coefficient, that gives me a statistic called the coefficient of determination, which gives me the percentage of variation in one variable explained by the other. Now note that correlation is not causation, and the directional effects that we try to conclude with correlation are not supported by the statistic itself. In fact, how we determine causation is through the design of the experiment. This course is going to talk about how we can create experimental designs to determine causation. It's the design of experiments course. That's kind of our purpose here. So this idea of correlation is not causation. Maybe one other thing I can add to it, and we'll talk about this more later in the semester too, but is correlation is not causation doesn't mean that correlation can never be causation. It's more along the lines of correlation is not enough for causation. Now this is the same thing for a t-test or a chi-squared test too. Just because you found a statistically significant difference between the variables doesn't mean that the independent variable caused the dependent variable to be different. Just because you found a relationship between two categorical variables using chi-squared doesn't mean that one variable caused the other one to be different. It takes a higher standard to establish causation. Now that doesn't mean that those analyses and even correlation cannot determine causation. It means that we need more information. Specifically, we need information about the design, and we don't just need the information, it needs to be designed well. The experiment has to be designed in such a way that we can then determine causation. So you've heard correlation is not causation, and I suppose talking about correlation in our review is as good of a time as any to introduce the idea that it's not just correlation is not causation. A better interpretation of that phrase is correlation is not sufficient for causation. But if we have a proper design, then correlation can determine causation, and hopefully that's something we'll get to later in the semester. So we've reviewed a bunch of these basic statistics that, again, hopefully you've already seen, and you can see I'm not going super in depth on these. I'm quickly hammering through, quickly talking about them and move on. But one thing that I do want to make sure we spend some time on is how do we make conclusions? How do we actually make conclusions based on the results of these and other statistical analyses? Now, a little bit of time now hopefully is going to pay out many dividends in the future, because this is something that you're going to have to do with every analysis that you do. You're going to have to make meaningful conclusions. So in the next section, we'll talk about how do we make conclusions based on the test, and hopefully it'll educate you. Maybe it's going to be a bit more review for you. That's why it's in our review section. But maybe not. Maybe it's going to be something, kind of the start of learning new stuff in the class is how do we write appropriate statistical conclusions. So we'll talk about that in the next video.